In this problem, we're asked to investigate the convergence of the series 1 over n squared as n goes from 1 to infinity. And so one of the first things that I did here is just go to a computer and start making approximations of the partial sums. So I did like the k equals 100 partial sum. In other words, the sum of the first 100 terms. And let me just back up for a second and look at this in expanded form real quick, just so we're all visualizing the same thing here. So I'm adding the first 100 of these using a computer, and I got 1.635 out of that. I then looked at the k equals 1,000 partial sum and got 1.644. This is encouraging because it seems like the sum might be settling down to some finite number. Take 10,000 terms, 1.645. Take 100,000 terms. That took the computer a few seconds to do. And 1.645 again. And of course, there are more decimal points here that are changing. So this is very encouraging. It looks like this thing converges. But to actually prove it, what I'm going to have to do is bring in a picture of the continuous function f of x equals 1 over x squared. And you can see that as the yellow curve in the picture. And then there are these rectangles. And what are those about? Well, the height of the first one is f of 1, which actually is that first number in our sequence. The height of the second one is f of 2, which is 1/4, and so on and so on. So the areas of these rectangles, because they have a width of 1, they actually correspond to these terms. So this first area is going to be f of 1 multiplied by 1 for the width, so that's just 1. The second one is f of 2 multiplied by 1 for the width, that's 1/4. The third one, f of 3 times 1, and so on and so on. I think it's too hard to squeeze these in here, so we'll stop at 1/16 for that one. Okay, so now we've represented our infinite series as a sum of rectangle areas. And what I'm trying to do here is prove that the sum of all these areas is finite. And I'm going to do that by comparing to an integral of this continuous function. But it's necessary to remove this first term because I don't want to talk about the integral from 0 to infinity of this function because it blows up at 0. Well, no problem. Here's how we handle it. I'm going to split off that first term. And now I'm talking about the sum as n goes from 2 to infinity of 1 over n squared, which means all the rectangles starting from the one that has a value of 1/4. Now all I have to do is show that the sum of those areas is finite, and I'll be able to prove that my series converges. So I just put a little cut line there, and the sum as n goes from 2 to infinity of 1 over n squared is going to be less than the area bounded under this curve. You can see every one of those rectangles is underestimating a little bit. So this is less than 1 plus the integral from 1 to infinity of 1 over x squared dx. And then I'll just go ahead and calculate that integral. And x to the negative 2 integrates to negative 1 over x. And I'm evaluating from 1 to infinity. Plug in infinity for the upper limit, and 1 over infinity is 0. Then I subtract what I get when I plug in the lower limit. So that's going to kill the minus sign, and that's a 1. So what we've just proven is that this sum from 1 to infinity of 1 over n squared is some number less than 2. If you want to get really formal about it, you can say that the sequence of partial sums must be an increasing sequence because all of the contributions are positive to those partial sums as n becomes larger. And I just proved that it's bounded above by 2. An increasing sequence that's bounded above is guaranteed to converge. That doesn't mean it converges to 2. It looks like it's some number pretty close to 1.65, but it's guaranteed to converge.